Okay, so for the week 2 tutorial, we have 4 questions uploaded earlier. So it looks very simple to learn questions, but we have a lot of techniques we need to review from these 2 questions. Let's first look at question 4. To find the Laplace transform of a function given here, ft equals ut plus 2t plus 3t squared. Here ut is a unit step. And secondly, let's check our results with the initial and the final value theorem. So you might have time to think about this already. So let's say we have the ut here given to be unit step. It's a good opportunity to review what we learned in the Monday's lecture, what are different types of the input function of different signal types. So here we have the step function. So what is a step function by definition? If we have step input, it means that we have axis to be 0 to t and minus 0. When time is smaller than 0, the step function has a value of 0. So ut has a value of 0. And at time 0, it goes to the m value, the magnitude of this step. And from 0 beyond, when time is larger than 0, the function value ut will be constant at m. So this is how we define the step function. And a special case is the unit step function. We can define the st to be the unit step function, which means that m equals 1. We just go from 0 to 1 to be the unit step function. This is commonly used as an input to the system. Okay, and then we have the second term here to be 2t. If you recall, if we have an input to be t, what it is, what's the function input like? This can also be another ut. We can actually write it as a u1t equals 2t. So if we have such function like this, it's a ramp input, as we discussed in the lecture as well, because it has this kind of linear shape. And the third term is a t squared, so it's a higher order related to time. Then we have this total format adding together 3 terms, and we want to get the Laplace transform. Recall that for Laplace transform, we can have the nice additive functionality, so we can add this transform together. We can actually do the transform on each term. Because we want to do the Laplace transform on ft, so we can actually separate them to do the Laplace transform on each item and then sum them together. With this, we are able to use our table to do a straightforward transform using existing known Laplace transformations. Okay, so recall that because these are so commonly used, we have the ut to be this step function. And for Laplace transform, remember a nice feature that it only accounts for the time equals or larger than 0. So on this right half plane of the space, we always have the unit step function to have the value of 1. So when t equals or larger than 0, we can just write ut, the input, to be 1, to be the unit value. And if we do a Laplace transform of a constant of 1, we call that a constant. When you transform it to Laplace space, it just becomes a constant over s. So this is the first item, we got 1 over s. And for the second item, the ramp input, we got 2t. If we do the transform here, you can also then check the table to see, okay, if I got my ramp input to be t, very straightforward, my s domain has a function value of 2 over s squared here, because the t transforms to s squared. Okay, and then the last term, 3t squared, this is a second order. I can still find my corresponding transform because you know we have the fixed format, if I got my time domain to be t to n minus 1, then my Laplace transform can be directly found from the table following specific format written here. So the order of the S variable is the same as the order is of the n here. Time to n minus 1 and ice to the exponent of n. Right? Therefore, we got the t square transformed to ice cubic here, because our n here is actually 3. 3 minus 1 to t square, and then here we got the ice cubic term to be the last one. And on the denominator, we just do the calculation to get 3 multiplied by 2, 1, to get 6 here. So this is basic calculation we're able to do for Laplace transform. We can get the time domain directly to the S domain. This has been practiced for many times, and you will use this again and again in the follow-up study. And then the second question asks us to check the results with the initial and the final value theorem. So we talked about these two theorems in class and in book as well. Let's have a quick review of what does these two theorems mean. So we emphasize this final value theorem a lot, so it's shown here. Why do we call it final value? It really means in the time domain, when time goes to infinity, we have this yt to reach the final state. So we have the limit t goes to infinity of yt defined as the final value, and its corresponding value in the S domain is equals to the limit of s goes to 0, the function value of sys. So this is a S domain correspondence. This is proved by the mathematical transformation. By definition, we can prove that. So this theorem means that we have proved that already. And then we want to use the theorem to check our results. We just do both sides, do the left-hand side, right-hand side, and see if the results are equal to each other. So first we got the original ft function here, and when t goes to infinity, this ut is 1, and 2t goes to infinity, 3t squares goes to infinity as well. Therefore, this time domain function has a value goes to infinity. You just sum, once you sum several terms together, either term has an infinity value, the whole function will go to infinity. So the left-hand side has this value, and right-hand side, we evaluate when s goes to 0, what's the function value of sfs. So we should write this down because we got the transformation already. So we got, this is our fs, and multiplied by this s term before. So if we multiply this by one item by item, we can cancel the first one, it becomes the value of 1. The second one becomes 2 over s. Third item is 6 over s squared. This is constant because when your denominator goes to 0, this term actually goes to infinity. This goes to positive infinity. And the same here, the denominator goes to 0, the third term goes to infinity. So if we sum these infinity terms together plus the constant, the whole value is also positive infinity. Therefore, we can say these two items on both sides are equal to each other. So that's how we check our results. The final value theorem holds for the results. Okay. And similarly, we have the initial value theorem here. This can be proved mathematically as well. We didn't talk about this in class, but this follows exactly the similar format to the final value theorem. The difference is for initial value, it means time goes to 0. So at the beginning, it is the initial value. At infinity, it's the final value. So for time goes to beginning, the function value of yt, the initial value theorem says is equals to s goes to infinity, the function value of sys. Right? So this can be proved by the definition of what is s, what is ys related to yt. But then let's use this to check our results. When time goes to 0, we got our initial value to this. And when time is 0, what's the value of ut? Remember ut, when t equals 0, it has the value of the unit as well, so it's still 1. And then this 2 multiplying t, multiplying 0, it becomes 0 directly. So sum together, it gets a value of 1. And on the right-hand side, when s goes to infinity, we evaluate this function value. We thought it seems straightforward. Oh, sfs, if s goes to infinity, well, the function goes to infinity as well. Not really, right? Because your fs is not bounded, so you need to calculate this still by the format of fs. So again, this is s multiplied by the whole term. Then you cancel s with the first item, and the second item become 2 over s plus 6 over x squared. And when your denominator goes to infinity, positive infinity, the whole term has a value to be 0. Similar here. Therefore, this becomes 1 plus 0 plus 0. The whole value is just 1. So again, these two sides are equal to each other. So this is how we say we check the results using the initial value theorem, and it holds as well. So we got confidence that our transformation meets both theorems. Okay, so this is the first practice. It just give you a function in the time domain. Are you able to get its transformation in the Laplace domain? And are you able to use the initial value theorem and final value theorem to evaluate your results? And sometimes you can also use this theorem to get your Laplace transform. Okay? So the second question, we also give you the statements very briefly, just 3 sentences. But before we go to the practice, I hope to get you to review what we learned in the lecture this week. Because it's very important, we need to refresh our mind first to say, what is the system response? What is a first order transfer function? So we can use this series to guide our application example. Okay, so here is a standard form of a first order transfer function. This is by definition how we define the first order transform. So first transfer function gives you the relationship between your output ys to the input us in the Laplace domain. So we have the y over s to be defined with this k over tau s plus 1. So still remember what these 2 important coefficients mean. What is k and what is tau here. So k is defined as steady state in here. And the tau is called time constant. So why do we call it a time constant? I want to show you it really has a physical meaning to be the time constant here. But first let's see if we got a step response to the system. So what we mean step response? All the examples shown in the class, either it's first order to reach certain steady state, or it's second order to have some oscillations. It all corresponds to a response of a step function. So our step function is the input to certain value. We define the step input ut equals m for t equal and larger than 0. And we see that this transform of a constant step goes to Laplace domain to be m over s. So this is our input to the system. And then we can say it's first order output, second order output, and has all these nice features. And the US is exactly in this same format. And if we want to evaluate what is the YS here based on the transfer function, we can then take the Y multiplying US on both sides. So we got to get our Y equals U multiplied by K over S plus 1. Because we know our input is a step function M over S, so we can directly multiply these terms together. That's how we got this YS equals Km over tau S plus 1 multiplied by S. Right? So this format is in the Laplace domain. If we want to get the time domain response, we can still go back to our table to find the corresponding format. And this is commonly seen as domain function. And we found that it's transformed to the time domain to be Yt equals Km multiplied by 1 minus e to the exponent minus t over tau. Okay, so we discussed in class, if we divide in Km on both sides, so we got y over Km equals 1 minus this exponent term. And we also discussed if time goes to positive infinity, it becomes a steady state value. So the y infinity is the steady state value of yt. By the formulation, we know that when t goes to infinity, this exponent goes to 0, so the y infinity has a value of Km. Therefore, this left-hand side, we can define it as a new y over y infinity to be our y-axis. And on the right-hand side, t over tau to be our x-axis. So we can plot this relationship on this plane. Then we show that this is t over tau equals 1, that means 1 tau of time. So here the tau is a time constant. It really means it can be the unit of time. So if the tau is 1 hour, this becomes from 0 to 1 hour to 5 hours. But when we write it, it's dimensionless because we use t divided by tau already. Right, so here it has certain meaning. Our time constant, if our tau is a large value, so this 5, if tau is 1 hour, then 5 is 5 hours. But if tau is very fast, it's 1 second, then my 5 is 5 seconds. But within this 5 tau time, our system is able to reach its, at 5 tau, say the y over y infinity is already almost 1.99 to the y infinity. So this tau actually shows how fast your system is reaching the steady state y infinity. Okay, so this is the basic concepts we discussed earlier. So based on this, we can then move to the question statement of this. So we have a stirred tank here of volume V. You can draw your own plot and you can define your own variables. So here we just use this plot to give you an overview of this problem. So if we have the stirred tank of volume V, and then if a stagnant pocket, so we show here, if a stagnant zone where no mixing occurs, exit here. So it's like a dead zone that is isolated from the surrounding liquid. How would this affect the response of the outlet concentration to a step change in inlet concentration? So before we go to the mathematical thinking, we can just do the physical, like to think about this in a real example. What does this mean? Just think about you got a bottle of water and then you put a stone in it. So this stagnant zone can just be a solid stone. And then if you inject some ink, some colored ink to the water, and you want to see how fast this colored ink will be reflected from your outflow. So this gives you the question, how will this stone, additional stone to your water system, to your liquid system, affect the transform of the concentration. This concentration switching from input to output. Okay, so you can think about how it will make it slower or make it faster. By God, we can have some answer. But then we want to show this using the transfer, using the whole series we have learned using the mathematical forms. Because if we just have one reactor, it's very simple. We can just think the whole process. But if we have a very complex process, it's very straightforward. We can tell by the mathematical transformation to say if my system is really becoming slower or faster. Okay, so this is why we love the tank, the stir tank here with the volume V as given. And as always, when we start to get the process, we want to draw the process diagram, we want to label all the important variables and parameters we know, and then we want to write down our mass balance. So here on the slide, I give you some of the mass balance equations, but this is not complete. So I want you to think about, if you want to write down the mass balance, how to do for this system. If you read from the figure, you can see that we define the inlet as a flow rate of W. It's a mass flow rate of W. And then the concentration of X1. So we define it as a mass flow rate and the mass concentration or mass fraction of X1. And outlet, we also write W and X. Why is this W the same as the inlet flow rate? So that's something missing here. We can just straightforward thinking. We know because the volume is fixed, so the inflow equals outflow. But when you do the mathematical writing, you still need to write it down the mass balance for the overall system. Because the overall mass equals the density multiplied by the volume. So it's my accumulation of mass equals B rho V over dt to describe the dynamic of the system of the mass change. And again, this accumulation of the mass balance equals what's the in? Here is a mass flow into a system minus outflow of mass. Because in this case, we know that rho, the density is constant, and V, the volume is constant as well. So this mass does not change with time. So this dynamic term is forced to be zero by assumption. Therefore, we have our inflow mass equals outflow mass. So we now need the definition. Then based on this, we define the in and out both have the mass flow rate of W. Okay. So this is the premise of all the follow-up analysis. We define the concentration and the mass flow rate here. But because the concentration is different, we want to analyze if the concentration change in the inlet flow, how will this influence the outlet flow? So we have the concentration change here, X1, X, those are time dependent. So we want to analyze the dynamics of those X terms here. Therefore, we need to write the component mass balance again. So again, it is a rho V to be the overall mass multiplied by this concentration. And because this concentration is changing, so the inlet flow is X1, outlet flow is X. if we want to analyze the system, the concentration within the tank, as the outlet, this is X, and in its flow system, we always have that the outlet is the same as the system itself, as the same as within the system. So we have the accumulation to be X over dt as well. So this X is my real-time concentration in the system. There's also the outlet concentration. So this dynamic will be equal to the inflow components, the flow rate is W, and concentration, my fraction is x1 minus Wx. This is my overall components mass balance. So here you can see component A because it only have one, like you can imagine as an ink or some certain chemical. So this is a component mass balance. And then we do some transformation, put it simpler. We divide the W because it's the same for both terms on both sides. And we got rho V over W here. And normally we want to group the coefficients together to define a new parameter. So we can group them together. And then here we define it as tau. What's the reason here? Why do we call this term tau? So tau normally means that time constant is tau as well. So we'll try to see if my new coefficient here has the same unit as time. What's the unit of this rho V over W? Because rho is density, V is volume, so this is mass. So it can be some unit to G, but the denominator is a mass flow rate, so it's some kg per hour. Therefore, you divide rho V by W. This term itself has a unit to be time. This is how we call this new term. This is a time constant term here. So if we define this rho V by W as tau, we then simplify the writing. Just use tau here. We got a new simplified representative of the mass balance. Okay. And now we are at the time domain. If we want to analyze the transfer function to study the dynamics, we need to turn the system to the Laplace domain. So we just do a Laplace transformation. Okay. And then we see it's a first order derivative. We check the table and found, okay, we got the first order derivative. Then if it's df over dt, it's similar here, dx over dt. Then I can just use my sf minus f0. So I just put sx in the s domain minus x0. Can I directly write my x0 to be the value of 0 to simplify it? So we have done this in all the equations. We hope to cancel the initial value to make it 0, right? But this term here, why we can write it as 0 value? This is some trick here. So we have discussed in class how we define a new variable, called the deviation variable. So we do not need to worry about the initial value. We try to make the initial value to be 0, so we can put this term. We can directly know this second term. But we cannot write it straightforward. We need to know how we get to there. So it's not a straightforward process, but we need to do it here again to say why we can directly write this term, the initial value to be 0. You recall that we define a new variable here, the deviation. We call it x prime. Be the value of the real x, so this is the real concentration, the real function, minus x bar. So what is x bar here? That's a steady state value at the initial. We could assume the system at the initial condition at the initial state is at steady state. Therefore, we can define this x bar to be a constant at the beginning, at the system's or beginning of the initial steady state value, or we call it nominal steady state. So here, because our x is a real value, so it's a dynamic term related to time, x prime is also related to xt minus x bar. So if we have this new definition of the deviation variable, if we take the derivative on both sides, we know that the x prime over dt equals x minus x bar over dt. Because x bar is a constant, so if we write this, separate them, one constant over dt, the dynamic term is 0 because it's constant. So we got the nice feature that this dynamic of dx prime is the same as the dynamic of x. Okay, so on the left-hand side of this original function is good. We can then write this as dx bar over dt. And then on the right-hand side, I want to use my x bar consistently. So I want to do a transformation here. You see, I have my x1 and x. Then if I want to follow this format, I can directly minus one term here. If I write this term, this equals x1 minus x1 bar, because it's x1, get this, and then we have minus 1 x bar. We need to add this term back to make the equation hold. So it's the same minus x. So this is the same as x1 minus x1 bar minus x. Put the minus sign out, it's 1 bar. So very close to what we want, because here is already the new variable of x1 prime. Right? But here is x minus x1 bar. So I want to get the uniform of the x prime. Then I need to see if I can get x1 bar to be some equivalent form. Because we know that x1 bar is a steady state value of x1, the initial condition. So again, back here at the steady state, our system, going back to the original format, our system is at steady state without this dynamic change. If we want to get a steady state value, we just put the dynamic term dx over dt to be 0. So at the initial steady state, this term equals 0. So the right-hand side, x1 steady state equals x steady state. That gives us a nice feature that x1 bar equals x bar. So this is very important, steady state value. We know that, so we can change here the x1 bar, we can change to x bar as well, because they are equal to each other at the bar state. And then this term becomes a new variable of x prime, right? So it's very good. We got the equivalent form from x1 minus x to be equivalent to x1 prime minus x prime. So we're confident to add this new variable here and then do the Laplace transform. Because for this x prime term at the initial condition, when t equals 0, this x prime 0 has a value of 0. So we can directly write the Laplace transform in this format. Okay? So this is the trick within the process. It's not just we directly write x0 to be 0. It's how we define the new deviation variable to make it 0. So you just recall it, we need to use it here. And since then, we have the nice formulation we write it back to x and x1, but it's actually the bar here, right? So we have the new variable, but because they have the same dynamics, we just minus a constant. It's just the same dynamic behaviors. So we write from the transfer function to this equation. And then if we want to get the relationship between the output and the input, we want to write our transfer function. So if you recall that ys over us, and here output is just our x, and input can be our x1. We divide x1s to the left-hand side, and then the right-hand side just 1 over tau s plus 1. Does this look familiar? So this is the format we have learned already. If we have the first order system, the transfer function is k over tau s plus 1. So this is, because this gain is a constant, so correspondingly in this system, we have the gain to be 1, and our tau here is the same, defined as time constant, v over w. As we discussed, this time constant as a unit of time. Okay, so by now we have got the perfect form of the transfer function. Then how can I use the transfer function to describe the dynamics of system? That will explain how my system will change corresponding to the in-light change. Okay, so now we start to go back to a system. If we consider regard this dead zone here, so my total volume, my effective active volume will actually decrease. Okay, so my V decrease. Because my V defines the time constant, so my tau will decrease as well if my V decreases. And my K is just a constant, it does not change. So if you recall what we drew earlier for the system response figure, for this first order process, we have the T over tau and the Y over Km, or Y over Y infinity. Okay, so we discussed that if tau is larger, it means that we need more time to reach a steady state. Well, here my tau becomes smaller, so within less time, because tau is smaller, so within shorter time, I would be able to reach a steady state. That's how my system response becomes faster because of this dead zone. Okay? So if you go back to think about physical meaning, it's straightforward. If I got some dead zone, some stone in my flow system, then what I have in the inlet will be transported faster to the outlet. So this is what the whole transfer function tells us here. Although for a single process, it's simple, but from this mathematical transform, if we have very complex process, we can then derive the transform function. So we are able to isolate the dynamic behaviors of the whole system to say how fast it will respond. So that's how we use the transfer function to really guide us to have better understanding of the system itself. Okay, so that's a content for this tutorial. We will then practice more examples like this. Thank you.